In this video, I'm gonna discuss Gauss law and its application. Its application. Before starting Gauss law, you should have known with electric flux. What is electric flux? Electric flux is the electrical energy associated with some surface or some volume. Suppose a Q charge is put inside a sphere, then the electric field lines from charge will come out from this sphere, and we can say that this sphere is linked with some electrical energy. So this electrical energy is just called electric flux. An electric flux is a scalar quantity. And its mathematical expression is flux is nothing but E dot ds or E dot A, means dot product of electric field and area of that surface through which electric flux is linked. Like in this case, the flux is linked through a curved surface or total surface area of given sphere, which is 4 pi r square. Suppose r is radius of this given sphere. Now we can move towards Gauss law. What is Gauss law? Gauss law in simple terms is an alternative way for finding out electric field, and its statement is like that. It states that the flux linked with the surface, E dot ds flux linked with the surface, is Q enclosed by the surface, charge enclosed by the surface over epsilon naught. This is mathematical expression for Gauss law. And in simple word, by using Gauss law, you can find electric field of different charge particles or different charge distribution. Like you can find electric field of point charge, linear charge, of some area having charge Q. By using Gauss law, you can also find electric field of some charge distribution like linear charge, surface charge, point charge, or volumetric charge when charge is distributed over a volume like solid sphere or hollow sphere. Now let's move towards Gauss law. How to apply Gauss law? I will apply this Gauss law in 3 steps. The first step will always be like finding Gaussian surface. Second step would be like applying Gaussian law, which is flux E dot ds equal to Q enclosed over epsilon naught. And the third step and the last step for applying Gauss law will be finding ds and Q enclosed. Okay. All right. Now let me explain what is Gaussian surface so that I can begin with how to apply Gauss law. Gaussian surface. Gaussian surface is a surface where electric field is constant. In simple words, like suppose a point charge having charge Q is placed in a room, and you have to find Gaussian surface for this point charge. As we move our distance in 3 dimensions from this point, you will get all these points have same electric field, which is kq over r square. When you join these points and find locus, you will find that it would come out to be a sphere. So the Gaussian surface for a point charge will always be a sphere. Similarly, the Gaussian surface for a linear charge will always be a cylinder, because all the points around the linear charge will form a cylinder. So we are known with that the Gaussian surface for a point charge will always be a sphere, and the Gaussian surface for a linear charge will always be a cylinder. Now you can apply Gauss law. The first step of applying Gauss law is finding Gaussian surface. Second step is like applying simple Gaussian statement, which is flux is equal to Q enclosed over epsilon naught, and third step is finding ds and Q enclosed. Let me show you how to apply Gauss law on point charge. Suppose this is a point charge having charge Q. So the step 1 will be finding Gaussian surface. So this sphere will be its Gaussian surface, which is R, which has R its radius. So first step is done, and second step is applying mathematical expression for Gauss law. E dot ds, which is flux of this surface, is Q enclosed by surface over epsilon naught. Now E dot ds, it is a dot product, then you should know its angle. What is angle between E and ds? The normal of surface will always be perpendicular to the surface, and electric field is also in same direction. So electric field and that normal vector is in same direction. Normal is the direction of this given area, so they have zero angle between them. So E dot ds is E ds cos theta, and cos theta is cos 0, so it will become 1. So it is simply E ds, and E is constant over the surface because it is a equipotential surface, and here and here at every point on the surface electric field is constant. So you can carry out E from the integration, and you can write E outside the integration, and with next step Q enclosed over epsilon naught. Now second step is done, and third step is to finding ds and Q enclosed. ds, area of Gaussian surface. In this case, the Gaussian surface has area 4 pi r square. The surface area of sphere is 4 pi r square, and Q enclosed by this Gaussian surface is Q. So we have done with our third step. Now let's put this value inside the Gaussian law. A is outside the integration. The area of integration is 4 pi r square, area of sphere, and Q enclosed is Q, and epsilon naught as usual. Here E come out to be Q upon 4 pi r square epsilon naught. 4 pi epsilon naught 1 over this can be written as k q over r square, and we have already seen this in Coulomb's law that electric field by a point charge is k q over r square, and we have also derived through this Gaussian law. So let me repeat once again what I did. I just find Gaussian surface in first step. For point charge, it will always be a sphere. In second step, I wrote simply mathematical expression for Gaussian law, and in third step I found out ds and Q enclosed. the ds for Gaussian surface is 4 pi r square and q enclosed by it is q. I just put inside the Gaussian law and I end up with electric field as kq over r square, and this is our required answer. Now let me show for a linear charge. Suppose a linear charge is given having linear charge density lambda. As I already told you that the Gaussian surface for a linear charge is always be slender. All the points which is around the linear charge will form a cylinder. And in this cylinder we have three surfaces, two circular surfaces and one curved surface. The circular surface have normal vector in this direction and in this direction, and that of curved surface will have normal vector in this direction, and normal vector is the direction of area, and the direction of electric field is away from the linear charge in perpendicular direction of charge. This is charge distribution over a line, and this is electric field of this distribution. For surface 1 and surface 2, the angle between area and electric field is 90, which is pi by 2. So when you put or when you find out flux through this surface S1, S2, so you have to find flux through surface S1 and S2. Flux is E dot A, which is EA cos theta. Here you put EA cos pi by 2, which is cos 90, and cos 90 is 0, and you would come out to be with result 0. Means the flux through surface S1 and S2 will be 0, and you have just left with surface area, curved surface area S2. Now you have to find the flux through this curved surface area. The flux through this curved surface area will be the flux of entire cylinder. Now step 1 is done, that finding out the Gaussian surface. The second step for applying Gaussian law is writing its mathematical expression, which is flux E dot ds is equal to q enclosed over epsilon naught. When you find ds, the third step, when you find ds, you will get 2 pi r l, which is curved surface area of cylinder. 2 pi r l. L is the length of cylinder. This is length L, and the charge is also, which is enclosed, is of length L. So the charge enclosed will be lambda times L. Simple unitary method. What is lambda? Lambda is charge per unit length. If unit length has charge lambda, then L length will have charge lambda L. So charge enclosed by the curved surface area is lambda L, and the area, which is ds, will 2 pi rl, curved surface area. So you can write ds as 2 pi rl and q enclosed as lambda into L. Now you can put these value inside the expression. E can be carried out outside the integration because it is constant over the surface. E can be carried out from the integration, and you will left with ds. The integration of ds means integration of small area, means finding the area of Gaussian surface, which we have already done, which is 2 pi rl, and q enclosed by the Gaussian surface is lambda times L upon epsilon naught. Cancel out L and L, and you will end up with lambda upon 2 pi r epsilon naught. This